Humans have always been interested in dissecting the universe. At the microscopic level, you realize that everything is just a bunch of molecules put together. At the nanoscale, molecules are made up of atoms. At the picoscale, all of them are essentially made up of the same things: protons, electrons, and neutrons. To probe even further, we realize that the protons and neutrons are essentially made up of the same types of components known as quarks. Could everything in the world essentially be different manifestations of the same thing? Quantum mechanics is the first theory that successfully explains matter at very small scales. Protons, neutrons, and electrons are known to many as the fundamental building blocks of all matter. However, as we look closer, it was observed that at such a small scale, these particles do not behave like discrete particles, but rather as waves. This is the origin of the wave-particle duality. As such, quantum mechanics was established by expressing particles as waves mathematically. Quantum field theory, however, sees things differently. If one encounters two electrons in the microscopic world, he will find that the electrons are completely identical, in the sense that if you swap the positions of the two electrons, no difference can be spotted. To explain this, physicists then theorize that the same thing, a quantum field, produces them. Imagine when you throw a stone into a pond. The ripples propagate in all directions, and the wave traveling to the north is no different from the one traveling to the south. If we liken the waves that propagate in the two directions to particles called phonons, the two phonons will thus look completely identical, except that they travel in different directions. In quantum field theory, transformations play a very important role. But before going into that, an understanding of Lagrangian is crucial. So what is a Lagrangian? The Lagrangian of a system is a physical quantity that determines how the system evolves over time. Systems with different Lagrangians will behave in different ways and thus must be different from one another. For example, imagine two bananas on two banana trees, one privately owned and another wild. The two bananas in two different environments will have different experiences. The one privately owned would be eaten, while the wild banana would remain forever alone and eventually rot. Poor thing. Back to transformations. Transformations, such as rotations, can be divided into global and local transformations. A useful transformation will be one that conserves the Lagrangian. To calculate the Lagrangian for our water waves, let's choose the center of the pond to be the origin. A global transformation will be like rotating the entire pond clockwise or anticlockwise, and it essentially does not affect the wave, but is simply a change of the coordinate system. As such, the Lagrangian does not change for all waves. However, a local transformation changes the pond differently at different points. Imagine rotating the waves at the center to a large extent and rotating them less and less nearer to the banks. The waves look drastically different now, and our Lagrangian will not be conserved under such transformations. To ensure that the Lagrangian of our quantum field is conserved under local transformations, we will need to use something called a gauge field. A gauge field is a field that, when added to our system, changes the Lagrangian in such a way that even under local transformations, the Lagrangian will be conserved. Let's go back to our pond example. While we rotate the center of the wave anticlockwise, let's also generate a hurricane over the wave such that it also rotates the wave anticlockwise, the only difference being that it rotates the wave more at the banks and less in the center. The wave would now be similar to having undergone a global transformation, and the theory we end up with is called a gauge theory. The hurricane we just generated is then a gauge field. In quantum field theory, symmetry breaking also plays an important role. Let's take a closer look at the water, which makes up the pond. For a box of water in liquid state, the water molecules move randomly, and let's assume that they can either point up, with the oxygen atom on the top, or down, with the oxygen atom on the bottom. When we flip the box of water, we can hardly see any difference. However, when the water is cooled below 0 degrees Celsius, it freezes and the molecules are arranged in such a way that they are either all pointing upwards or downwards. When you turn the box upside down now, the orientation of the water molecules will definitely be different. If we represent what is happening on the graph, in the liquid state, the potential energy of the water box looks like this, and the energy is lowest at the overall orientation that neither points up or down. Just like how a ball will roll to the bottom when you place it in a bowl, our box of water will automatically go to the state with the lowest potential energy. However, when the box is cooled, The potential energy looks like this, and the lowest potential energy is the orientation that either points up or down. Our system can thus, by chance, end up in one of the two minimum energy states, which are very different. The symmetry of an upside down flip no longer exists and is said to be broken. Since we are not applying any transformations, this is called the spontaneous breaking of symmetry. It breaks itself. In the quantum picture, assuming we have a system of two fields, psi1 and psi2, and their potential energy graph looks like a Mexican hat, now imagine that the graph is actually a mountain. At the start, we place a giant rock on the peak of the central mountain. If we shake the rock slightly, it will fall all the way down to the rim of the valley, in an arbitrary direction. Since every position in the valley has the same energy, there's a spontaneous breaking of symmetry. From the top view, if we push the rock along the direction of psi1 or psi2, in both scenarios we experience resistive force because of the increasing potential energy in these directions. However, if we redefine our fields by relating psi1 to psi2 and then splitting them into a radial and tangential field, a movement along the tangential field will not experience any resistance, but a movement along the radial field will need us to push harder. The tangential field can be thought of as a massless field, and the radial field will become more massive. In addition, for this massless field, we call the particles generated by it Goldstone bosons. Bosons are particles with spins of integer values, where spin is another intrinsic property of particles, just like an electric charge. We have discussed about spontaneous breaking of symmetry and gauge fields. What if we put these two together? This will just be like moving the hurricane we had previously to the valley. Guess what would happen if we have a hurricane around the rock in the valley? It would now become difficult to move the rock in the tangential direction as well, as if the gauge field eats up the massless Goldstone boson and becomes massive in the quantum picture. This process of eating up a Goldstone boson is called the Higgs mechanism. Now I'll introduce the Higgs field. What is a Higgs field? A Higgs field is a specifically defined quantum field with fixed charges, hypercharges, and so on. The particles that it produces are called Higgs bosons. A Higgs field, just like any other field, can undergo spontaneous symmetry breaking. When a Higgs field interacts with a gauge field, the Goldstone bosons in the Higgs field are eaten up, making the gauge field massive. Examples are Z0, W+, W- bosons, and photons. The massive Z and W bosons can only travel through space over a small distance before decaying away, and thus the forces they carry, the weak nuclear forces, are only short-range. Another boson, the photon, does not eat up the Goldstone boson in the Higgs field, since there is no more of it after the consumption by Z and W bosons. They remain massless, and that is why the forces they carry, electromagnetic forces, can reach much further than nuclear forces, to infinity and beyond. By saying a specific boson carries the force, we just mean that the forces between two objects are due to their interaction with this boson. The quantum field theory has many other interaction pictures, and they collectively complete the standard model, one that unites three of the four fundamental forces: electromagnetic forces, weak, and strong nuclear forces. However, particle physics is facing a huge problem now. Even though we are able to unify three of the four forces, we are still unable to fit in the biggest piece of the puzzle: gravity. And that is such an embarrassment since it is one of the first few forces that we are acquainted with in daily life. Simply adding a graviton, a hypothetical boson that carries gravity, to the picture does not work. Some calculations will lead to answers that approach infinity, which does not make any sense physically. Neither does the standard model explain why cats sometimes behave like liquids. Another problem is the mass of neutrino. A neutrino is predicted to be massless in quantum field theory, however, it was found that a neutrino does possess a non-zero mass. Dark matter and dark energy are also not explained in the standard model. 96% of our universe is believed to constitute of dark matter and dark energy, while normal matter only constitutes 4%. More information regarding them might be available in the future with the completion of the upgrade of the Large Hadron Collider this year. In the LHC, physicists have been able to collide particles with extremely high energy together, and many bosons and fermions, including the Higgs boson, have been discovered. The LHC is just one of the many stepping stones for us Homo sapiens to understand our mysterious world. Despite the tremendous efforts by our predecessors, the paramount secrets of our universe are still undiscovered. The entire world of physics might just be waiting for the flash of one single idea. Join us, for it might be that flash of light